We're going to show you how to make a brake test machine, mostly how not to make a brake test machine. And the second part of this video is we're going to ask you how to build a drop test tower. We just cleared out the area and we're pretty excited to show you our blueprints and find out what you think they should be. So stay tuned. Hi, I'm Ryan Jinks, and welcome to our new lab where we have our Slacksnap machine here at my welder's house who made this thing. And we're gonna build a drop tower here and hopefully get this squishing machine to work. Because who doesn't wanna see climbing gear squished in reverse? I have been asked many times now how to build one of these. And there are a couple variations and varieties out there. And I'm gonna show you what I have and kind of how it works. You've seen it in videos, but I'm going to go into more of the details on what you can do and what not to do in order to make your own. As you've probably seen in many of our videos, we had a pulley system and a Costco winch, which was very clever, I might add, but that was me trying to avoid using hydraulics, which we finally have now. They are also pros and cons and limited, and we kind of found a hack between pulleys and hydraulics, so I'm pretty excited to share that with you. I definitely need to give Bobby credit for that. That was all his idea. Now, as you can tell, this is a horizontal brake test machine. What you can do if you're limited on space, floor space, you can build it up, but you're very limited on what you can do. I really wanted a longer one so we can do stretchy samples, but 90% of the things you would break, you'd be able to do if this was 3 meters high or 10 feet high. The framing can, I just have a lot of access to aluminum here because Larry welds a lot of aluminum. And so it kind of looks like this on the inside of this. But there is an architectural version of this that has rounded edges, which would have been really nice if I knew that when we were building this, because that sharp edge is just, I don't know, not as friendly when we're trying to wrap things around it. But we've made this work just fine. And we did 45-degree welds. It's worked out great. We put some solid, oh my gosh, that's slackliner. Put a solid steel bar going all the way through. In order to prevent this from bending, Larry added these collars on here, which has a threaded hole for these bolts to go on the back of this plate right here, which is now loose. And that is what we built this whole thing around, this dynamometer. Now, this is a crane scale, and it has done so well, but we are moving up in the world, and we'll show you that in a minute. This has the same thing on this side. This is basically our attachment point, and we use this similar concept of being able to hold this in place, and this goes all the way through to the back side. And we ended up having to reinforce this with some extra material because, as you can see, this is thinner. Because we don't have a dynamometer with a specific hole size, this ended up bending. And so we had to increase the size. So anyways, you have to have an attachment point. Now that I'm not using a Costco winch, which is where this was sitting, this guy down here, you could basically, if you had like, let's say the architectural tubing, you could wrap literally a spanset, 4 times, 6 times over and make that connection point right there with a big shackle, and that would be fine. So the inside working space I have is 16 inches and love it. I don't think I would go with smaller. 14 inches would be the smallest I would want. And because these are 2x4s, true 2x4s, that's 20 inches. But because I have a beam right there and I have sawhorses that kind of come out, this pretty much takes a footprint up of about 28 inches. Now this thing does jump around a lot because it's big and you're putting a lot of force on it, and we built it in 2 parts so it's easy to transport, even though I never transport it, so I would probably not do that again. But we put some climbing hangers here, some AMC, and then we have some turnbuckles which have worked themselves loose now, and that kind of keeps it from jumping around too much. But we did make use of the fact that we had bolts here by putting hangers here. And we also put hangers on the inside in order to hold our hydraulic, because when things break, things go flying, and that's something that's very important to remember. Let's talk about the hydraulic cylinder real quick. So a little bit of anatomy, since this isn't that hard, but it wasn't explained that well in the research I was doing. This is the cylinder, this is the rod, and the stroke is the distance you have to work with. The stroke or distance we can pull here is 60 inches because it's not all the way quite out, and it'll stop right there when it gets sucked in. So it has a piston, which will be round because the cylinder is round inside of here. And you put oil on this side and it pushes it this way. If you put oil on this side, it's going to push it that way. And that is the basics of how hydraulics work. Now, before I show you the actual fluid system, I love tie rods. Tie rods is where you got the rods tying this plate to that plate over there. The reason I like that is because it's square and it sits on the ground very well. It's not round. Round is really great when you've got a tractor or something else where you want less of a space. But these are cheaper because they're easier to service. You just unscrew these nuts, pull it all off, and it's not all built in. And it just works really, really good, as you can see how we secure it this way. Now, on the side we put as the bottom is where the fluid goes in. And so we have fluid coming in on this side, and we've got one on that side. And then we've got our pump here that will pump fluid this way or this way. Now, I decided to put quick connects on everything because we pull this apart and we travel with it. And this is the pump that we use on our BoltBuster cylinder, which is bigger than this cylinder, which we have found to be strong enough, especially when we use our pulley mechanical advantage with it. Now, DC. Now, this is something I wish I knew. This is a DC powered pump. DC, direct current, means batteries. This is designed for a dump truck, for example. And so they make a lot of these. But if they make an AC or alternating current to where you could just plug it into the wall directly, they assume that you're using it all the time. So it's made for higher frequent use. And because it's such a much smaller volume of units they make, they're not as affordable. I think this was $400-ish. And I already had this battery from my van. I didn't need as many batteries in it as I had. Now, because of my van, I have this awesome golf cart battery charger. Because I don't have a solar system, I don't really van life enough to justify doing all that. So this thing will charge up this battery quite quickly. And I really like this thing. The problem is this was $400. This made sense for my van, but now we've just increased the cost of this whole system. But I was reusing stuff I already had, and that's why we got to where we're at. So I just plugged that in, and it's reading the batteries. So it says there's 30%. It could easily jump to 60 once it's, yep, there we go. And it's charging up our battery, which is powered to this. This just came like this, so we didn't have to do anything more than attach it to the battery. So you can hear this noise, and we typically unplug it before we film, so you don't have that in the background. But you can run this whole thing while it's plugged in, and you're not using the pump enough for it to burn out per se, because you have to prep the samples, then you gotta record the samples, and you have to write it all down and get the next one installed. And so by the time you're done doing that, you're only pushing the button once every 10 minutes. Speaking of the button, we added the cable to it because I want to stand on this side of things when I'm pushing things. And so this is my safety wall. And that is where I put the laptop because I needed a place to put this anyways. Now, I really like that speed. If you're breaking stretchy things, this is an awesome speed. So this is rated for 3,000 pounds. It's a 3-inch bore, which is inside of here. And our stroke, we already said, was 60 inches, and the rod diameter is 1.5 inches. And with that, we get a speed that I like. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000, 8, 1,000. 8 seconds to move it 1 foot, which is fantastic when you're doing stretchy samples. Now we put a pressure gauge on this, and we only get 2,000 PSI out of this pump. And this is 5,000 pound rated hoses and 3,000 pound rated cylinder. And so we are not maximizing this. And so we're only getting, after testing it, 48 kilonewtons before it stops. So something else that took a lot of time is making sure that I got the right fittings. It's just really hard to get all of these to be compatible. Now, if you hard hose, I was going to say hardwire, if you install the hose directly, you're going to eliminate some of these pieces. But I really like the fact that I can just pop this, put a paper towel under it, and capture some of the oil. Now, a little trick, because we're usually outside, is I use vegetable oil. Pretty funny. And that allows us to be a little bit more biodegradable than just using hydraulic oil. Maybe I lose some force doing that, but I don't care. Before we get into dynamometers, here is our BoltBuster hydraulic. You can see here our fitting. It's kind of getting a little gunky. And we have a 2-inch rod, so it's bigger with a 5-inch bore. You can see it is pretty large compared to our other one. And we have a 2-foot stroke, which means the back of the piston is about right there. But that is very limiting if you have a lot of slack in the stuff you're connecting to bolts. So sometimes we have to connect soft releases to pull all the slack out of the system. The reason I don't want this in Slacksnap is it's too slow for anything stretchy. If we're gonna break soft shackles, it's fine. But if we're trying to break webbing and ropes, it just takes too long. So let's discuss dynamometers. This is our new one. This is rated for 20,000 pounds, and it's going to a lab jack that's in here. Marcus Bird put this together for us. Still got to play with some engineering stuff to get it to play nice with the laptop. But anyways, this lab jack T7 Pro can read the changes in the voltage very quickly. And then the laptop will spit out the number of the force that we get. Now, all of that is done inside of these other dynamometers, but they all have limitations, generally speed. We're going to go over what we've been using, what I like and don't like. But we're going to be eventually upgrading to all of this soon. And what's nice about these is they swivel instead of having to put 2 shackles to each other. And if you don't try to embed this in the system and you kind of create something that grabs or whatever, you can bolt, you can, however you want to build a connection to the back of this machine, you can basically just attach the shackle however you want to possibly just a industrial sling on the end. So we have a 20,000 pound crane scale and a 10,000 pound crane scale, and you don't want to go over them. There's just not a lot of wiggle room, especially with the screen. This is rated, it will not break until it reaches 80, 90, 100, or 110 kilonewtons like we got in our tests. It's the new line scale 3 really rated for 90, but if you take it above 30, the screen will start to crack like we had in a video that we had before. Now, all of these dynamometers read fairly slow. This one is 500 times per second. This line scale 2, I believe, is 40. The line scale 3 is going to be 1280, which is amazing. This is probably 10 or 40 or 10 or 40. These are really slow, but when you're doing slow pull tests, it doesn't really matter. But for drop tests, these won't cut it. So that's why we had to upgrade, just like I was forced to upgrade to hydraulics eventually. I zigzagged towards success. It's kind of annoying. So I have terrible news for you guys. This is not going to cut it. The line scale 3 is an awesome line scale coming out. You can get them in pre-orders. No shame here plugging this. However, I don't know if it's the right tool for you to have any brake tests, unless you're going to break things that are under 30 kilonewtons, and I've had carabiners break above 30, let alone webbing and ropes. It just, if you put a rope in a loop, it could possibly be stronger than this, at least what it can read. This only goes up to 20, and believe me, you do not want to take it above 20. That's super annoying about this. It's maybe great if you're rope jumping, but it's not great if you're trying to actually break something. These are durable. I'm so impressed how well they've done. On BoltBusters, we put this thing on its side and pull it, and that's what you're watching in our videos. But eventually, you're going to be looking at the laptop numbers and the graphs and us pretending to be more science-y now that we have this guy. And we're going to have to figure out how not to damage this connection right here. So crane scales have always been my best option without knowing anything about fancy dynamometers. Once we perfect this, I'm hoping to make the code and the software and everything open source, so you can literally buy an S-beam, you can buy a T7 Pro lab jack and just plug it in. Okay, so you have a 20-foot rectangle. You're stoked. On the bottom side is just plywood, by the way. Forgot to mention that. That's how that looks and works. And you have hydraulics here. You got your pump, you got your battery set up, and now you got your dynos. So there's a lot more to this. You have to, in my opinion, you really should film the samples so you can go back and look. I'll never remember everything we've ever broken in here, but when you can see a video, it's way more thorough than what you can write down in a spreadsheet. On slackline.com, we have our entire spreadsheet on there and all of our videos. So if you want to look up a sample number, you can see what we did. You can only write down so much in the spreadsheets, but you also have to do the spreadsheets. I recommend you date them. I don't think we did that when we started, and kind of want to write down everything you can. Being super thorough about writing the data down is pretty important if you're going to use the data. Now, sometimes it is nice to just come in here and just break something. You don't write anything down, you don't film anything, and you're not trying to be sciencey. That is actually a lot of fun. But as soon as you actually try to make progress in knowledge and want to share it, it does add a lot of extra work. As you can see right here, we have these lights, which I have this DC converter from the AC power that it's plugged into in order to have DC current coming through the LEDs, which means they're constantly bright for your slow-mo enjoyment. Because we tried in the past to use LEDs and they would flash, because I think it's what, 60 hertz they flash out, and we're filming at 960 frames per second, or 32 times slower than real life. So that's why you're all getting seizures in some of those old videos. So we finally figured out this, got the light directly over where we will be filming. The hydraulic is a lot easier to reset, so Bobby's not having to pull the pulleys back to reset everything. You just push a button. Now we're going to brake test a carabiner that was donated to us. This is an old steel carabiner that I have a feeling is going to be pretty strong. So maybe it will max out our hydraulic here, and then we'll show you how to do our mechanical advantage hack in order to get, I don't know, a lot more bang out of the buck you spend on this smaller, cheaper, better for us hydraulic.
So what am I doing in this?
I'm just seeing what.
Bumping my head.
Oh, I didn't put that high enough, did I?
You didn't.
Well, I needed the light to be lower.
Ryan height.
I actually, yeah. Look, I don't hit it at all. All right, so we now have a span set connected to this, and in a U shape. It's probably stronger than the carabiner. We swapped this out, so we got the 20,000 pounder, or 100 kilonewtons, because this could break over 50, which will be fun if it does. What's this basket, Bobby?
So these are our miscellaneous working span sets.
Span sets?
Span sets are these things. There's one of those in there. There's not anymore. What do you call these things, Ryan?
Soft shackles.
Soft shackles.
Yeah. So, something very important. This. If you don't use that, this goes flying that way, and that goes flying that way, which is much more consequential when you have a 50-pound block of pulley sitting there.
Yep.
So, how do you connect this carabiner to such a large shackle?
So we're going to use a soft shackle to the hard shackle to the carabiner.
Now, what is the size of this thing? Some people complain that it's too wide instead of like a rope being inside of here, but I don't know a rope that would break this anyways. We also have thinner ones that we could double wrap, but then that makes it just as wide as this. But you have to have a whole accessory of things. And so we have under here our garbage pile. some webbing and ropes for miscellaneous tests. We've got, I think I did a video on this. I know I at least broke them. Paracord, there's all sorts of stuff we're constantly using. Bobby's gear that he donated to break. And then we just have a lot of AM steel for, a lot of this is BoltBuster related, but we have to sometimes bridge the gap between here and there. Now the spanset's nice, but it is not very adjustable. So you're kind of stuck between this size, or this size. And yeah, there's just a lot of connections you need in order to make every sample work. This one is this big. Some things we break have a web lock here and a web lock there, and you have to have bigger space. And then you don't want to suck up and lose 12 inches of this just to pull, let's say, this out of the slack if this is going to be stretchy. Now, this is not going to be stretchy, so it's not a problem for us to pull it in a little bit. So a little hack here is before you turn on the camera, unless you're explaining how to make brake test machines, you put it up to 1 or 2 kilonewtons, make sure everything looks good, make sure you got your catcher, make sure everyone's out of the room. I don't like to have a cover on this because we have cameras on it. So we just basically don't stand in here when we do dangerous things. Right, Bobby?
Right.
We try not to. It is pretty funny. Larry will be out watching and he'll like hide behind the big machine over there, but he wants to see it. I'm like, you don't see brake tests. I watch brake tests in the videos like you guys do. I don't stand here and go, "Ooh, whoa, look what's happening." Okay, so that's locked. This is not up against the spine. What do you think about that? You think?
That's where it's going to get loaded.
That's
It
true.
loaded itself there.
Yeah, that's true. So we are at 1 kilonewton. Now, filming is a big part of this, at least in our world, right? So what we built here is a little bit of a hack in order to eliminate having tripods right here where we're trying to work. So I'm very excited about this part. And then we can either film sideways like this, or I can put the thing just a little bit more over it and just set it down, maybe zoom in a little and film that. And this is very adjustable where I put this and what angle and how I film it, so you guys can see what's going on. Now, because this carabiner is sideways, it might be nice to just film this here, or at least put the slow motion here, and then put this camera like this. And it does block the light a little bit. And we can always add a soft shackle if we want this to be orientated more flat-like. So in case you didn't know, for us to break 6 samples takes us, what would you say, 2 hours sometimes?
Yeah, it depends on the sample. Sometimes a lot more.
Yeah, it's setting up is a lot. Making sure it all gets filmed, catching it. So, and you have to anticipate, this is not likely to break, but what if this breaks versus this? Now, if this breaks down here, this is going to go with it, and all this is going to go flying that way. So you kind of have to anticipate how things are going to go. My plastic boxes are bomber.
I've got like 8 inches of steel between me and that, like a tank.
That is terrible. 23.94. Oh,
shocking.
And it shot, oh my God. And then if you're going to film brake tests, always act super shocked on every single one so people get excited about it. Wow. Would you look at that? Neato. Would you whip?
Yes, but I sure wouldn't carry that.
For the value of 24 kilonewtons.
Based on other steelies that we use to test stuff all the time, we were expecting around 50 kilonewtons minimum for this.
Yeah, these are 72, just for record.
So that's pretty shocking that it's kind of half what we were expecting for very similar size.
The material felt very similar,
Yeah.
like heavy, solid. Okay, so we were trying to impress you with our 48 kilonewtons maxing out and that steel carabiner being stronger than it was. So we just connected directly to this, this is very unlikely to break to the hydraulic. Go for it, Bobby. So you can hear. Oh, wow.
Keep going.
Okay, stop. So as you can see, when Bobby's pushing the button, it doesn't go anymore, and the pump just makes funny noises. We basically have maxed it out, and I'm not going to stand any closer to this than I am at 50.78. That's 10,000 pounds of force on the span set right now. So back it off. Keep going. So, pretty impressed by the span set. It feels like it's been at 10,000 pounds. So how, Bobby, do we get more than 10,000 pounds?
Get ready for this. Blinding flash of the obvious. We do a 2-to-1 with this, which theoretically doubles the strength.
All right. How do we do a 2-to-1 on this?
So,
Because it wasn't blindingly obvious to me. All right, so these are from Tractor Supply. This is like not... Everyone said this would break, and guess what? They're still with me.
So 2-to-1, as I understand it, you have one side anchored, which we will take this and anchor it back to the bar there. And then you pull on the other side, putting twice the force on the sample that you're pulling on.
And you have to have a shackle here. This has the risk of going flying. It does add complications to it. You definitely don't want it in the system if you don't need it. But let's find out how strong it is. Since our thing isn't long enough, we just doubled up the span set over our bar. Soft shackle at the end of this. This is only going to see half of the force we put on the system. So we ran it through the pulley, and then we have to add shackles. Put that directly into the pin. And that's the thing about using big things like this, is you have to go from giant to smaller until you get to your sample.
I keep that out here so we don't forget it.
Yeah, because we don't know if this is going to break. What are you building, Bobby?
So I am building a soft release.
Why?
Because it's one of the strongest things that we know how to build easily.
Yeah, I don't know what else we would break right now that would be stronger than...
Wanted to break a smaller shackle.
No, let's do a soft release.
Soft release has the advantage of you don't have a bunch of metal going flying at 100 kilonewtons.
I see some metal in the system. But yeah, that's not going to break. This in theory would. So now mini soft releases, that is a sew-in loop, but it doesn't have to be in order for it to work. And if you go around a couple times, it increases the strength relative to the amount of times you go around. See how he's pulling on that? It takes out all the slack. And when we're doing BoltBusters, this can be very helpful because it's as strong as we need it to be. And we can have a couple kilonewtons before we even start pulling on our 2-foot stroke, which is our other hydraulic cylinder. That's your second, so now you're going to be going around a third time. And every wrap is basically 20 kilonewtons. So, yeah, this is an amazing, amazing tool in the brake testing world. And in slacklining in general. You just unravel it when you're done, after it's got a lot of pressure on it. And you can unravel your slackline or your brake test machine if, for some reason, you cannot release the pressure. Yeah, that's what I do.
Okay, so this is 2 half hitches.
It's 2 half hitches. It's kind of can make it hard to untie later, but we're not doing that right now. Cool. So put some newtons on there. I don't think we need this. We're not going to stand next to this. Do function peak hold.
Is this 0?
Function peak hold. Okay, 1, 4. Okay. that's why we don't stand next to this stuff. We didn't think it would break, so we didn't put a catcher on it. And this went flying. And if it hits our rod feels okay. It could. Dang it. All right. We need a stronger soft release. While Bobby is setting up our new and improved soft release with more wraps, something I want to mention is when you do put a 2-to-1 on here, you have to use half of your, if you use all of the stroke, you're only going to get half the distance. And that is the problem with any mechanical advantage and leveraging anything is you're going to definitely lose the amount of stroke you're able to maximize. But anything you're breaking that is this strong is probably not going to be stretchy. So we found this meets all of our needs for Slacksnap. How many wraps are you trying to do, Bobby?
5 or 6. I think we got 4 on the last one.
Yeah, if we got 6, it would be for sure bomber.
All right, there's 2.
I mean, this is basically one of the weakest webbings out there, too.
Yeah.
So great.
That's 3.
What I like about using this to film is it's attached to the wall and not the brake test machine, because this thing jiggles every time something goes a-flying. Okay, I was not about to stand next to this with 96.38 kilonewtons or 21,700 pounds of force. That's impressive. And yeah, that is what you can do with a 2-to-1.
It's got shoot up here. Yeah, I totally did.
Oh.
Here, underneath.
Oh, wow. Oh, when we didn't catch it in the before, this thing went flying and hit that connection and dang it.
We can show this other one.
All right. So this one got worked hard, but this one here is untying just fine.
So 4 versus 7 wraps.
Another fun fact. This point right here is going to see the full force, right? And this is going to see half the force. This is going to see half the force. However, this metal is now bent funny from the shackle. So, and this is rated for 20,000 pounds. And we took it to, oh yeah, it did really good considering we just maxed out that pulley. Here's a fun thought experiment. If you can only use, in this case, this will be a 1, 2, 3, 4 to 1. And so what you can do is you're only going to get half of this 60-inch stroke. So not even half, you would get a quarter. And so about right here, if you fixed this eye to right here, and it went through 2 pulleys, the thing is you would have to have a pulley here and you would have to have it fixed. You might be able to put a bolt all the way through and some hangers, come to a point and hover that there, allowing them to be there, and they would slide, and then you would pull, and you would only get to pull maybe to here. So you'd want to pre-tension everything, but you would get 200 kilonewtons if you did that. And we technically actually put this, I believe, over what it's rated for, because it's a 20,000 pound dynamometer. Oops. So this is after several years of me using pulleys with trees, and then using pulleys in a rectangle, and now using hydraulics and pulleys. And I'd like to know your feedback on ideas. Please don't tell me to use AC powered hydraulics if they cost $2,500. But I mean, throw me ideas. I'd love to banter with you about this. If you want to see more details, I don't even know what else I'd add. Let me know and I'll help you design yours. All of this works in the same way if you stand it upright. You just have to make sure things don't go flying. And that's something we're going to be practicing and thinking ahead on the drop test tower, which is going to be next, so we can get some of your feedback. Let's go outside. This is beautiful if you know what you're looking at. It's a little windy, so let's just see what we can do out here. and we're going to use this space for the drop tower. Now this concrete slab is concrete's crappy and it's about 3 inches thick. We might add concrete footings on top, 10 foot by 10 foot setup here. This is the spot it's going to be. Now, let me show you a couple things. So this is the space I'm trying to work with. It's nice to have the few feet here, and then everything will be on this slab. It'll probably go, let's say, here to there, to there, to there. And then it's going to go 45 feet up here. I'll show you why and how we're going to do that. Probably be about the same height as that tree. So we want a nice firm base so nothing's gonna rock over. Let's go back inside the lab here. So we have 20-foot tall beams that we are going to recycle that he has on this property already. And they're steel beams. I'll go show that to you in a bit. But the top is what I'm curious about. Let's see here. I do over. I am no artist, but so far so good. Now we're gonna have the posts here, here, and here. And I wanna make sure we have enough space in the middle for human testing. And what we're gonna build is a truss right about here, down to here, and do some truss stuff in order to put our bolts and our anchors right here. Now, this is 20 feet up at this point so far, and this will be 5 feet higher. And that gives us, when we're standing on our little platform or space net or whatever we build right here, a comfortable working height for this spot and somebody to stand here and stay up here and maybe even walk around to this side to put the camera. Is that a camera? And then, because we want to shoot the samples this way. Now, what's going to bring our sample up is a crane of sorts, like a hangman. And I'd like this to be adjustable this way and that way. And then we can do like a telephone pole style ladder. As far as getting up here goes, we would just put a permanent ladder on the side. And this would be 20 feet higher than this point. And you're gonna lose some in pulleys and releasers or whatever. And so you're gonna get to drop 15 feet of the samples before you have to allow some space at the bottom for stretch or whatever, because we're probably going to have mattress or something at the bottom. Hopefully, I have no idea what we're going to do for a catching system. Now, to stabilize this, I might just take this all the way over to here and also do this, and then we can pick where to put our hangman and then drop the sample. And sometimes we will release our sample level with our bolts, and sometimes we'll go to a factor 2, and sometimes we'll do a half of a factor and see rope stretch and samples and size and whatever. But what's nice about being able to move this back and forth is that we could drop samples here, which allow a bit of a swing to see how much that affects it. One question I'm curious about is if this truss is right here near the edge of the structure, where there will be strength, it doesn't allow much for things to be swinging underneath. I don't want too much of the samples to be on these crossbars that hold the whole thing up. I was thinking maybe 1 or 2 feet in is where the truss would be, and then I could just space net here so we can comfortably work and hang out next to where the space is, which would, this will be, let's say 8 feet. If this was a 10 by 10, we have 8 feet in here in order to have stuff fall through a big giant hole. If this truss is 2 feet inside. Now, if any of this makes sense to you, now that we've got so many lines, please give me your feedback on how we can make this better. So these are the posts. These are 20 feet tall and some pretty thick steel. And so I don't think they're gonna be going anywhere when we do our drop tests.
So we went back and looked at the footage you saw 10 minutes ago, and the pin, which goes here and catches here, broke, which allowed this to release, and that's when we had failure.
So it was 23 kilonewtons strong open, because it's technically what an open carabiner would be like. Mmm. Interesting.